In this video, we'll do a quick review of some of the ideal gas processes we talked about in the previous videos. We will be dealing with conservation of energy for closed systems, that is, systems that do not have mass entering or exiting the system from the system to the surroundings. And we always have the energy balance equation, that the change in internal thermal energy equals energy in terms of heat in minus the energy in terms of work out of the system to the surroundings. Since the systems are closed, they contain a constant number of defined moles of the defined gas within a homogeneous volume. There are four processes we talked about in previous videos: isothermal, isochoric, isobaric, and adiabatic. I've shown four energy system diagrams below each of these types of processes, with the solid gray line showing the system and the volume of gases contained with the system, and the dashed gray line is the boundary interface between the system and the surroundings. In the previous videos, I talked about ideal gas compressive processes, in which the final volume is less than the initial volume. In this video, we'll talk about the reverse of that, where it's the ideal gas expansion process, where the final volume is greater than the initial volume. What I'd like you to do is, for each of the system diagrams for the four different processes, is to draw arrows showing the delta U, the change in internal kinetic energy, the work term in terms of energy, and the energy in terms of heat term arrow for each of these processes, showing both directionality and relative magnitude. So pause the video and complete that, and then we'll start back up. The drawing of the directionality of the energy terms and the relative magnitude of these terms should only take you a couple seconds for each one of these processes. Starting now with the isothermal expansion process, you can see that the final volume is greater than initial volume, and the darkened blue line is following an isothermal line, or constant energy state line, from the initial state to the final state and all intermediate states. The first energy term to deal with is the change in internal thermokinetic energy. We know since the temperature didn't change, the internal energy didn't change for this isothermal process, so therefore delta U equals 0. For any process, the work out is the integrated quantity under the pressure curve for all the intermediate states from the initial volume to the final volume, as shown in the equation and is represented by the gradient area. Since for an expansion process, the final volume is greater than the initial volume, the work out is positive. And therefore, in the energy state diagram, I'm showing that the work out is positive, so work is leaving the system and going to the surrounding. The system is doing positive work on the surrounding. Now, referring back to conservation of energy, since there is no net change in internal thermal energy, and energy in terms of work is going out, we need energy in terms of heat to come in. So the Q net in is shown as heat coming into the system of the same magnitude as the work going out. In the beginning, there's a little bit of trick, because for isochoric system or constant volume, there is no such thing as expansion and compression. But for the example shown, I'm showing an example where the final pressure happens to be less than the initial pressure in this constant volume process. Referring back to the isothermal lines, we know that as you get closer to the origin, that the product of the absolute pressure times the volume is in the final state is less than the initial state. Therefore, based on the ideal gas law that PV equals nRT, we know that T is less. And at the final state, the product of the pressure and the volume is less. Therefore, the temperature dropped in the process as shown. Therefore, the internal kinetic thermal energy at the final state is less than the initial state, so delta U is less than 0. And therefore, I'm drawing the blue arrow is dropping. The internal thermal kinetic energy drops for this isochoric process when the pressure drops. Work is the integrated area under the pressure curve. For the change in volume, for the isochoric process, there is no change in volume, and therefore work out is 0. The change in the internal kinetic thermal energy has dropped in the system, and work out is 0. Energy in terms of heat had to go out or leave the system. Therefore, Q net in was less than 0 as well. And the directionality of the yellow arrow is showing energy in terms of heat leaving the system to the surrounding at the interface. And it's the same magnitude as the delta U term. Looking at our third process now, for isobaric, or constant pressure process, I'm following a red line with increasing volume because of expansion at this constant pressure. As you can see, based on the isothermal curves, the temperature of the system in the final state is greater than the initial state, which agrees with the product of the absolute pressure times the volume in the final state being greater than the initial state. Therefore, the internal kinetic energy at the final state is greater than the initial state, and delta U is greater than 0. So therefore, the blue arrow showing an increase in internal thermokinetic energy inside the system. The final volume is greater than the initial volume, so therefore the system is doing work on the surroundings at the boundary, and so the work out is greater than 0. And so my black arrow is showing energy in terms of work is leaving the system. And since the internal energy went up, even though energy in terms of work went out, there had to be a lot of heat coming into the system. So therefore, the yellow arrow is the sum of the blue and the black arrows. And the energy in terms of heat in is positive, as the surroundings is putting energy in terms of heat into the system at the interface boundary between the surroundings and the system. If you recall from the isobaric video, the ratio of the energy in terms of heat in compared to the delta U is the ratio of C sub P to C sub V. And the ratio of delta U to work is the ratio of C sub V to R. And for the last expansive process, adiabatic, we're going to explore, the system follows the magenta line as it expands, where the magenta line is the isentropic or constant entropy line. By definition, we know for an adiabatic system, there is no heat transfer between the system and the surrounding. Therefore, energy in terms of heat equal transfer is 0. We can see that in the final state, in all intermediate states, the temperature is less than initial states. Therefore, delta U is less than 0. And since the final volume is greater than initial volume, the work out is greater than 0. And the magnitude of the work out is equal to the magnitude of the change in the internal kinetic thermal energy.